Okay, in this lecture we're going to finish our section 4.3 material on partial derivatives. And in this part of the lecture we're going to be talking about higher order derivatives of these multivariable functions. So as we can recall from Calculus 1, well, we could find the first derivative of a function, which was itself a function. And so we could then find its second derivative or third derivative or fourth derivative and so on. So let's consider defining higher order partial derivatives for functions of two or more variables. So the simplest case that we'll look at to introduce the idea is the case that we have a function of two variables, say f of x and y. So in this case, we would define the second order partial derivatives of that function f as follows. So let's introduce some notation here. First off, we can use the subscript notation that we've been using for partial derivatives. So f sub xx would denote the partial derivative of f with respect to x, then differentiated again with respect to x. Or using the Leibniz notation, we could say we would differentiate with respect to x the partial derivative of f with respect to x. Or we could rewrite this as del squared f over del x squared. Similarly, we could define the second order partial derivative of f with respect to y, f sub yy, as representing the derivative of the partial derivative of f with respect to y, differentiating again with respect to y. So that is, using the Leibniz notation, the partial derivative with respect to y of the partial of f with respect to y, or del squared f over del y squared. Now we can define similarly f sub xy or f sub yx as the partial derivative of f first with respect to x and then with respect to y, or first derivative with respect to y and then second derivative with respect to x. Or using the Leibniz notation, we would have the partial derivative with respect to y of the partial derivative of f with respect to x, which would be denoted as del squared f over del y del x. Or similarly for f sub yx, that would be the partial derivative with respect to x of the partial derivative of f with respect to y, or del squared f del x del y. Now, these last two second order partial derivatives, f sub xy and f sub yx, are what are called the mixed partial derivatives of that function of two variables, where after our first derivative, we switch what variable we're differentiating with respect to. Now, a little bit about the notation, a word of warning here. If we're using the subscript notation, say f xy or fyx, the order of differentiation is determined by reading the subscript from left to right. So for instance, f sub xy is found by first differentiating with respect to x and then with respect to y, or f sub yx would be found by first differentiating with respect to y and then with respect to x. However, if we're using this Leibniz notation, notice that the order that we've written this was as del squared f del y del x. However, that is used to denote differentiation first with respect to x and then with respect to y. So if we're using the Leibniz notation, we want to read the order of those variables from right to left in those del expressions of our denominator. So similarly here for this last one, del squared f del x del y means first we differentiate with respect to y and then with respect to x. So let's look at some examples of finding these higher order partial derivatives. So in our first problem, we're asked to find all second order partial derivatives of this function f of xy. So let's start with the first order partials. We would have the partial of f with respect to x given by 2xy plus cosine of x plus e to the 3y. And the first order partial of f with respect to y would be x squared plus cosine of x plus e to the 3y. And then the derivative of that inner function with respect to y would be 3e to the 3y. So writing that factor out in front of our cosine, we have x squared plus 3e to the 3y, cosine of x plus e to the 3y. So now let's start finding our second order partial derivatives. Here, the second order partial f sub xx would be found by taking the partial of f with respect to x and then differentiating with respect to x a second time. So that would give us 2y minus sine of x plus e to the 3y. And similarly, the second order partial f sub yy is found by taking the first derivative of f with respect to y and differentiating with respect to y again. So the x squared term would have a derivative of 0 with respect to y. And then using the product and chain rules, we would have 9e to the 3y times cosine of x plus e to the 3y minus a 9e to the 6y sine of x plus e to the 3y. Now for our mixed second order partials, let's say f sub xy, we would take the partial derivative first with respect to x. So we're starting with f sub x, and then we would differentiate with respect to y, which would give us 2x minus 3e to the 3y times sine of x plus e to the 3y, making use of the chain rule there. And the partial derivative of f sub y, then with respect to x, would give us f sub yx. So again, we start with the first order partial with respect to y, and then differentiate with respect to x, which gives us a 2x minus the 3e to the 3y sine of x plus e to the 3y. And then the derivative of that inner function with respect to x is then just 1. So these would be our second order partial derivatives of that function. Now, one thing to notice here, if you look at the mixed second order partials, the partial derivative f(xy) and f(yx) are the same value. So this might start to raise the question, well, will those always be the same? So to try to address that question, well, let's look at some other examples and see if they are the same. So for our next problem, we're asked for the mixed partial derivatives, so just the mixed partials here, of f of xy, which is the natural log of x squared plus 3xy. So starting with our first order partial derivatives using the chain rule, the partial of f with respect to x would be 2x plus 3y. So that is the derivative of the inside function divided by the inside function. And the partial derivative of f with respect to y would be given by 3x over x squared plus 3xy. Again, the derivative of the inner function with respect to y divided by that inner function. So to differentiate and find f sub xy, I'm going to take the first order partial f sub x and then differentiate with respect to y. Now looking at the form of f sub x, to find this derivative, we'll have to use the quotient rule, which says we first take the derivative of the numerator with respect to y here. So we would have 3 times our denominator, x squared plus 3xy, minus the numerator, 2x plus 3y, times the derivative of the denominator with respect to y, which would give us a 3x. And this is all over the denominator squared. So simplifying a little bit, through the numerator, we have a 3x squared plus 9xy minus a 6x squared plus 9xy all over our same denominator. So combining some like terms, we can see that our positive and negative 9xy will cancel, and we're left with negative 3x squared over the denominator squared. So simplifying a little, let me write it up here, negative 3x squared over x squared plus 3xy quantity squared. Now the partial f sub yx is found by first taking the partial derivative with respect to y and then differentiating with respect to x. Now again, here we'll have to make use of the quotient rule. So we differentiate the numerator with respect to x, which would be 3, times the denominator, x squared plus 3xy. And then we subtract the numerator, which was 3x, times the derivative of the denominator with respect to x, which would be 2x plus 3y. And this is all over the denominator squared. So comparing this expression with the answer that we had previously, well, our denominator is the exact same. In the numerator, we had 3 times x squared plus 3xy, and then we were subtracting the product of 3x and 2x plus 3y. So after simplifying, we get the exact same expression that we had for the partial derivative of f with respect to x and then with respect to y. So for both of these partial derivatives, again, we obtain the same value. So let's look at one other example to compare these mixed partials. Here, again, we are asked to find the mixed partial derivatives of arctangent of x squared y. So first differentiating f with respect to x, well, the derivative of the arctangent function is given by 1 over the variable x squared y quantity squared plus 1. And then we multiply by the derivative of the inner function with respect to x by the chain rule, which would give us 2xy Or simplifying just a little bit, we have 2xy over x to the fourth y squared plus 1. And for the partial of f with respect to y, we have, again, 1 over x squared y quantity squared plus 1 times the derivative of the inner function with respect to y, which would give us an x squared, or simplifying x squared over x to the fourth y squared plus 1. So now to find our mixed partials, well, let's start with f sub xy. So I'm going to take the partial with respect to x, which was shown here, and then differentiate with respect to y. So again, using the quotient rule, the derivative of our numerator with respect to y would be 2x times our denominator minus the numerator, 2xy, times the derivative of the denominator with respect to y, which would be 2x to the fourth y. And then this is all over our denominator squared. So expanding, we will have a 2x to the fifth y squared plus 2x minus 4x to the fifth y squared, all over that same denominator squared. So grouping some like terms, well, our 2x to the fifth y squared minus 4x to the fifth y squared leaves us with a negative 2x to the fifth y squared plus 2x over this x to the fourth y squared plus 1 quantity squared. Now, looking at the partial f sub yx, we start by taking the partial derivative of f with respect to y, which was found here, and then we differentiate with respect to x. So again, by the quotient rule, the derivative of our numerator with respect to x would be 2x times the denominator, x to the fourth y squared plus 1, minus the numerator, which was x squared, times the derivative of the denominator with respect to x, which is 4x cubed y squared, all over our denominator, x to the fourth y squared plus 1 quantity squared. So expanding through the numerator again, we have a 2x to the fifth y squared plus 2x minus a 4x to the fifth y squared, all over x to the fourth y squared plus 1 quantity squared. And combining these terms, 2x to the fifth y squared minus 4x to the fifth y squared, we're left with a negative 2x to the fifth y squared plus 2x for the numerator. So we get the exact same expression that we had previously. So in all of the examples that we found, these mixed partials have been equal to one another. So is that always true? Well, not necessarily, only for relatively nice functions. So the following theorem, known as Clairaut's theorem, says if a function f of xy and its partial derivatives with respect to x, with respect to y, and the second order partials, or second order mixed partials, are all continuous on some open disk centered at a point x naught, y naught, then the mixed second order partials of that function will be equal at that point. So this gives us conditions for where those mixed second order partials will equal one another. And the condition for these mixed partials to be the same are that the function we're differentiating, along with its first partial derivatives and those mixed second order partial derivatives all have to be continuous. So as long as we have relatively nice functions, then these mixed partials will be the same. And I'll mention, for the purposes of our course, the functions that we work with are always sufficiently nice such that these mixed partials will be equal to one another. So from this point moving forward, we will always assume that those mixed partials will be equivalent. It takes a very nasty function for those mixed partials to not be equal. Now, in the last part of this section, we'll consider higher order derivatives, not just, say, the second order partials, but maybe moving into third order partial derivatives. So in this first example, we're considering the function f of xyz, which is equal to e to the xyz power. And we're asked to find the partial derivative f sub yzy of xyz. So that is the third order partial derivative, where the order of our derivatives is given by first with respect to y, then with respect to z, and then with respect to y again. So let's start with the first partial derivative that we're looking for. That is the partial of f with respect to y. So using the chain rule, well, the derivative of e to the xyz would be e to the xyz times the derivative of the inside with respect to y would give us x times z. So moving to the second derivative, f sub yz, well, we now need the product rule and the chain rule. So differentiating our first factor, xz, with respect to z, we would have an x times our second factor, we leave alone, e to the xyz, and then I would add x times z times the derivative of e to the xyz with respect to z, which would be xy times e to the xyz power. Or simplifying just a bit, well, I see that I could factor out e to the xyz from each factor, and I would be left with x to the first plus x squared yz. So for the third order partial derivative that I was after, that is f sub yzy, we would need to make use of the product and the chain rules again. So the derivative of our first factor, e to the xyz, with respect to y, is xz, e to the xyz power, times our second factor. And then we add the product of our first factor, e to the xyz, times the derivative of the second factor with respect to y, which would give us x squared z. So again, to simplify, we could factor out an e to the xyz from both terms. Distributing this xz through to our set of parentheses here, we would have x squared z plus x cubed yz squared, and then plus I have, after I factor out my exponential from that second term, x squared z. And finally, combining these x squared times z terms, I have e to the xyz times 2x squared z plus x cubed yz squared. All right. So as one last example, we have the following function, u, which is defined as the natural log of x plus 2y squared plus 3z cubed. And I'm asked to find del 3u, del x, del y, del z. So using the Leibniz notation, this is asking for the third derivative of the function u, where the order of differentiation is given first with respect to z, then with respect to y, and then with respect to x. So first, let us find the partial derivative of u with respect to z. So by the chain rule, we would have 9z squared over x plus 2y squared plus 3z cubed. Now, the next order for the derivative would be with respect to y. So looking at the partial derivative of u sub z, then with respect to y. Well, using the quotient rule, the derivative of the numerator with respect to y is 0, and then we would subtract the numerator times the derivative of the denominator with respect to y, which would be 4y to the first power, all over the denominator squared. Or simplifying a little bit, we have negative 36 yz squared over x plus 2y squared plus 3z cubed quantity squared. So finally, to get the derivative that we're interested in, that is u sub zyx, we would use the quotient rule to differentiate the derivative u sub zy then with respect to x. So the derivative of the numerator with respect to x is 0, and then we would subtract the numerator. So subtracting a negative 36 yz squared gives us positive 36 yz squared, times the derivative of the denominator with respect to x. So by the chain rule, we would have 2 times x plus 2y squared plus 3z cubed to the first power times the derivative of that inner function with respect to x, which would just give us a 1. And that is all over our denominator squared. So we now have this polynomial to the fourth power. So simplifying a little bit, well, I recognize that I can cancel 1 power of x plus 2y plus 3z cubed from the numerator and denominator. And then in the numerator, I'm left with 36yz squared times 2. So I have 72yz squared all over x plus 2y squared plus 3z cubed to the third power.